All right, well, so let's get to it. So where were we last time? We were looking at the the bubble sort algorithm um, with our playing cards, and we saw just sort of experimentally. So let me, for those of you who are at home, not Chrome, we want Safari. I need to open Safari. We need to do window capture. Oh, it's got the correct window. Excellent. So let's blow this up. And let's go to our Google Sheet and just kind of look at Dr. C's Casino. So, um, the bubble sorts I had you guys do by hand was just for 5 and 10 cards. And let's kind of recap the data we saw. That what happened when you what happened when we doubled the number of cards? Did it double the work? It more like quadrupled the work. Okay, roughly. Um, and especially on average. Now, it's not like it's going to automatically quadruple the work, right? What happens if you just by dumb luck get a list, or sorry, what happens if you put your cards out and they just by dumb luck happen to be sorted in exactly the correct order? Well, then you only have to do n minus, well, 4 comparisons if it's 5 cards, or 9 comparisons if it's 10 cards, right? Which is a lot lower than the average amount that it took to actually do the sorting, okay? Now, the minimum numbers, there are, like I said, exactly that, just those are the minimum numbers that you guys got. So this did not is not the ultimate minimum necessarily, um, for this algorithm, because you guys, none of you happened to get them all in order when you dealt them, right? I mean, there was what, a 1 in 120 chance that you would have. If I had you guys do this a whole bunch more times, then probably eventually that outcome would have happened. But it didn't with our trial. Okay, so at this point, we could sit around sorting cards all day, and I could say, all right, do it for 15, 20, 25, 30, and so on, right? But as you guys could probably suspect, this is going to start to take forever, and we're no longer going to get the benefit of doing this with the cards. Okay, so if we're not going to do it with cards, what are we going to do instead? Well, we have, how many computers are sitting up here on this table? 1, 2, 3, 4, 5, 6 if you count the Apple TV, 7 with my phone, 8 for my watch. Right? We got lots of computers up here. So let's use a computer to do this. All right. So let me open up a program I wrote to actually do this sorting, and I want to explain how it works first. Um, So let me get it open, and then those of you guys who are at home, I'll explain or get the input switched over so you can see what I'm doing. Okay, so I'm actually going to put that here on the left, and then on the right, I'm going to put a terminal. Okay, and then those of you who are at home should be able to see both my screens, but let's just double check. Moderator, Prof. McKinney. Turn off the audio. Okay, looks good. Um, okay, so I wrote this in Python just because it's quick and easy and quick and dirty. Um, and the other reason I like Python is, well, the you guys may have noticed that for the iteration and the recursion assignments, like I gave you something that looks kind of like code. It is actually valid Python, right? So you could take that and actually execute it in Python as a way to double check your stuff. But the other benefit is that, well, while yes, Python is code, it is a lot more human readable than, say, Java or C++. There's no curly braces all over the place to kind of obfuscate things. But anyway, so what did I do? Well, the first thing I did was I defined a function called BubbleSort that actually will implement the BubbleSort procedure. Okay, so what do I give this function? I'm going to give it an array. An array is just a list of numbers, okay, in some sort of order. Now, for the purposes of this program, particularly when I'm, say, doing like 20 or 30 cards or, more than 13, when we were doing this with the cards, we had essentially 1 through 13 of each suit. Instead of worrying about that, I just put it in like, if I'm doing 30 cards, I'm just going to think of them as cards 1 through 30 and not, ace of spades, king of clubs, any of that nonsense. The idea is exactly the same, but it just is easier to define if it's just a sequence of numbers. Okay, so what is this thing going to do? Well, the first thing I'm going to do is I'm going to say, how long is the array? Okay, and my algorithm needs to know that because it's going to do something based on the length. Okay, and then the other thing I'm going to do is set the number of operations to 0 because, well, I haven't done anything yet, right, before. So the actual sorting will happen here, okay? And so what is this first bit going to do? Well, this first bit is going to basically scan through all the cards. Okay, so for I in range n-1, that means it's going to go from 0 to n-1, okay, which is a little annoying. So what's the very first number in my list? Well, okay, it would be, if I had, say, cards 1 through 30, I would have the numbers 1 through 30. But what are their positions? Their positions 0 through 29. Okay, so that's just sort of a thing you get used to in programming, that often the first entry in a thing is really the 0th entry. So we start counting at 0 instead of at 1. Just get used to it. It's yeah. Okay, so it's going to scan through the and do something basically for all of the different cards. And then the inner for loop, so notice here I've got 2 for loops, one of which is inside the other. And where the magic happens is here. Okay, so you know what, let me switch the projector over to, I don't know if the thing will work today. Let me switch that projector over so it's not so distracting. Okay, so the inner loop is where the magic happens, okay? Because right here, I have to make a comparison, okay? So R of J plus 1 are 2 cards that are next to each other. And R of J is in the spot just before J plus 1, okay? And what I want to know is the thing in spot J bigger than the thing in spot J plus 1? If it is, I need to swap them. Otherwise, they're in the correct order and I can move on. Okay, and this line right here is what does the swapping. Just kind of look at it for a minute and convince yourself that, yeah, that actually makes sense to swap things. Okay, does it make sense that that probably swaps the 2 items? Yeah, good. Okay, so that actually does the swap, and it only happens if I need to. And then the line right below it, well, if I just did a swap, I just did something, so I should add 1 to the number of operations that I performed. Okay, does that kind of make sense? So this is the bubble sort algorithm that you guys did with the cards, but just programmed in general. Okay, good? Yeah? All right, so, um, and then what I'm going to do is this function is going to return the number of operations that it took to sort that particular array. Okay. Now, I don't really care what the array looks like to start or to finish. I just care for now how many steps does it take for me to sort this thing. Okay, so does that make sense? All right, so then next, what I'm going to do is I'm going to define what's the length of the array that I want to work with. Okay, so for, let me change this to 5, and this will be basically the same thing as when you guys did this with 5 cards. Okay, this 10,000 is how many times I want the computer to do this. Okay, so I had each of you guys do it 3 times, right? And it took us, what, 10 minutes or something? So I'm going to have the computer do it 10,000 times, and it'll take like 10 seconds, right? So you guys are scrubs. Um, Then I'm going to say, okay, the minimum ops and the maximum ops, I'm going to start with some initial values. And of course, the total number of ops is 0. And then I'm going to do this procedure 10,000 times. I'm first going to define a random permutation. Okay, so I've got my array of the numbers 1 through 5 in this case. And so that means I have a list 1, 2, 3, 4, 5. Well, I need to shuffle it. Okay. And so the thing I'm going to use to shuffle it is this Numpy random permutation, which is just a function built into, there's a Python library called Numpy that's got a bunch of mathematical stuff in it. There's also a SciPy for doing a bunch of scientific computations. Anyway, so I just loaded that in and then used its function that I give it an array and it jumbles it up for me randomly. Uh, Now, I should say, is this random, like truly random? It never is with a computer. It's as close to random as you can get with a machine, a deterministic thing. Okay, but random is never truly random on a computer. And if any of you guys have played, like Diablo or something, you know that. Or, does anybody play like Stellaris or Crusader Kings or something like that? Yeah, the RNG giveth, the RNG taketh away. So yeah. Um, anyway, so it's if for our purposes, it's as random as it's going to get. Um, okay, and then I'm going to take this randomized array and sort it and count the number of operations it took to do so. We'll get whatever we get. Okay, and then we keep going, scrolling here. And then I'll add 1 to my number of operations. Or sorry, I've got a total number of operations. So what I'm going to do is I'm going to total up the number of operations it takes for all 10,000 times. And then at the end, I'll divide that total by 10,000 to get an average. Okay? And then the last little bit here is if the number of ops it took was bigger than the previous maximum, I should set the maximum to that new value. And similarly, if the number of ops it took for that one array was smaller than my previous minimum, then I should change the minimum value to that number. And then at the very bottom here, I just print everything out. Okay, to the console. Okay, so no big deal. So let me go to all right, so is the text big enough that you guys can read it okay? Yeah? Okay. All right, so let me save this since I changed the oh, come on. Oh, crap. That's right. I never installed Numpy on this laptop. All right, excuse me a moment. So I realized I installed it on my new laptop, but not my old one. So I'll just download and do that real quick. Um, yeah, that's the one thing I needed, right? Was so, um, well, actually, so here, let me, while that's downloading, let me go in and modify the code a little bit. Um, so I could, for example, um, let me save a copy of this so that I don't destroy what I've done. Okay, and then I'm going to get rid of this because I'm not using it. I'm going to get rid of the doing this 10,000 times bit, which means I need to untab all of this. So let's just do it for one array. And okay, so oh, and then let me delete that part. Okay, so if I run this for a single array, so let me say start with numbers 1, 2, 3, 4, 5, then I'm going to have to do how many operations uh, at minimum there? Okay, I don't know why that's happening. What the heck? That's going to be one of those mornings, isn't it? Oops. I think part of the problem is the cable's loose. Stay. Good dog. Okay. So uh, the the maximum number ought to be, well, okay, so what's printed here is the minimum, the average, and the maximum. And if, of course, I've only done this one time, then all three of those numbers should be the same because I haven't repeated the procedure. Okay, so why is it 10 when we thought it should be like 4 or 5? Well, let's go back and let's look at the actual sorting algorithm to see why it's the case. This loop, okay, so how many cards do I have if I'm doing it? Got 5, right? So that outer loop runs how many times? Okay, so for I in range n minus 1. So it's going to go 4 times, okay? And then the inside part is going to run how many times? Well, that's a little harder to answer because um, look at what it says. For j in range 0 to n minus I minus 1. All right, so we got to do a little bit of thinking here. When n is, or sorry, when I is 1, then, or 0 actually, I guess to start, then the j thing is going to go through the cards 0 to n minus 1. Okay, but as I sort things, I can ignore progressively more at the end of the list because I've already got the stuff at that end sorted, right? Okay, so that inner loop is going to start looking at everybody, but then it's going to wind itself down to where it's only looking at the very front end, okay? And that's why it's adding up to 10 and not 5. Okay. Right. Now, that when I say that, in this particular case, because our array started sorted, do we have to do any of this? No, we have to check whether or not the two things are the same. That's why I put this operation right here above the if, because I still, no matter what the order is, I still have to check if the two cards are in the correct order, right? That took work. The ops plus one that's on the inside is only if I do a swap, okay? So in the case of my array 1, 2, 3, 4, 5, how many swaps do I need to do? None. It's already in order, right? But how many comparisons do I have to do to check? It turns out in this case is 10. Okay, does that make sense? Sort of? Okay. So let's change up the thing while I get the installer going. Sign my life away. Okay. So while that's running, let's change the array and let's actually make it the worst case scenario. Oops, where it's in reverse sorted order. Okay, this is going to be the maximum theoretical work that we could possibly have. Okay, and that takes 20 operations. Okay, but let's come up with something that's jumbled up, but not worst case jumbled up. Like let's say we had 3, 1, 4, 5, 2, say. All right, how many steps is that going to take? Only 14. Okay, so between 10 and 20, 10 would be our minimum, uh, and 20 would be our maximum for the 5 card situation. Okay, does that kind of make sense? All right, so what do we think it's going to be if I made this an array of 10 elements? Okay, so 1 through 10. Okay, so what do you guys think the minimum is going to be? Okay, fine. What about the maximum? Oops. What's the comments in Python? Huh? Oh, right. Yeah, that's okay. Sorry, I've been doing so much stuff in C lately where it's double slash and um, yeah, okay. So, all right, so let's do that. And there we go. So at maximum, it took 90. Now, what's one thing to notice there? What's the maximum versus the minimum? Yeah, it was double that time. It was double the time before. That's kind of interesting. Okay, so are we finished with our installation here? Almost. Well, let's make another. Let's make it longer. All right, so let's do 11, 12, 13, 14, and 15, and then comment out this one. Okay, it took 105 at minimum, and how many at maximum? 210. It is double again. Okay, nice little pattern going on there. Okay, and hopefully this dang installer is almost finished. Just like watching a pot of water boil, right? What's the saying? Watched pot never boils. Okay, so now we should be able to go back to this one. Okay, why did that not work? I'll probably have to restart or something. Okay, well, you know what? Whatever. It's not important. Um, because what I did was in my casino. Oh, yay! We've got 2 more spammers in the chat. Hooray! They're gonna sell me um, yeah, free users and stuff. So let's see, how do I ban these people? Ban, ban. All right, excellent. Okay, so what I did was I ran through, okay, and I had my little program do this 10,000 times each for 5 up through 50 cards. Okay, so and what did we get here? Um, well, and so it was 10,000 times. All right, so look at the minimum versus the maximum. Now, I should say this was the minimum that occurred, not the theoretical minimum like we were talking a minute ago. So with 10 cards, what did we say our theoretical minimum was? I think we said 20, was that right? And the maximum was, what was it? I don't remember. Okay, but point being, when I see 48 there for my minimum number with 10 cards, that was the minimum number that actually occurred out of all 10,000 trials, not necessarily the absolute minimum that could theoretically happen, because these were just random shuffles of the deck, and I never ended up with the 10, 9, 8, 7, 6 right situation. It just didn't occur in those 10,000 trials. Okay, so let's just kind of look at the numbers that I've got there. So I've got the minimum, I've got the maximum that actually occurred, and then I've got the average over the 10,000 trials. And I just ran this and then copied down the numbers into my spreadsheet. And so let's kind of see what we've got. Well, the other thing I did, and why will become clear in maybe a little bit here, is I just calculated the number of cards squared. Okay, we saw last time that, you know what, there was like how much when I doubled the number of cards, how many more steps did you guys count? It was a factor of like 4-ish, right? Okay, well, that sounds like an n squared kind of thing to me. Okay, so I just said, all right, let's square the number of cards and let's compare all of these numbers to the square of the number of cards. And then I'm going to graph all this stuff. All right, so let's look at the graph. All right, so take a minute and just kind of stare at it because there's a lot going on. Okay, do they really have to do network stuff while I'm trying to teach? Just the number of cards squared. That's it. So nothing fancy. Just basically just y equals x squared is what I graphed in blue. Okay. Um, all right. So the minimum, and I wish the colors were actually in the opposite order here, but whatever. The minimum number is red. The maximum number is green. whatever, and then the average is in yellow. Okay, not shockingly, where is the average between the min and the max? That's good, right? We would have a problem if that weren't the case. Um, but what do you notice sort of about the shape of all of these graphs? They're all basically the same, right? Okay, yeah, the n squared is slightly above all of them. Okay, so in terms of like, think back to like algebra in high school or pre-calc or something. Um, how do you take the graph of y equals x squared and kind of flatten it vertically? You just multiply by some constant, right? So if you multiply by 1/2, it just squishes the thing vertically by a factor of 2. Yeah. Okay, so would you guys accept that based on this evidence, the green, yellow, and red curves are all just sort of squished versions of y equals x squared? Yeah? Okay, now guess what that means we get to do? Math. You guys can't see the smirk underneath my mask here. All right, so let me switch the input over to the iPad. All right, so you should be able to see a blank screen now, those of you who are at home. So what's the math here? Well, we've noticed that um, our average number of sorts and the maximum that occurred and the minimum that occurred, let's concentrate on the average for now, basically looked like n squared. Okay, so let's make precise what do I mean by basically looks like. All right, so okay, these things have to be non-negative functions, but that shouldn't be a huge shock because we're, huh? Oh, you guys can't see what I'm doing. Now let's try this again, shall we? There we go. That's better. Uh, okay, so what we're going to talk about is what's called big O notation. So if I've got two functions, f of n and g of n, and I've written them here as f of n and g of n because in math class you tend to write f of x or something like that, but what's the assumption about x? It can take on a whole ton of values, say even values between 0 and 1. What are the functions that we'll have to deal with in computer science, like mathematical functions? Well, they can only take in integers, right? It doesn't make sense to talk about sorting 12.3 cards. It does make sense to talk about 12 or 13, okay? So if I have two functions, I'm going to say that f of n is big O of g of n, means that there's some constant so that f of n is always less than or equal to that constant times g of n. Okay, so does the definition kind of make sense? And I know it's math class and you guys didn't think you were signing up for that, but Towski Shitsky, as they say in Poland. Um, okay, now why do we care about this for what we're talking about? Well, what do you think the bubble sort algorithm is? It's O(n) squared, okay? And we've got our graphical evidence for that, right? Because what did our graphs look like? Well, the blue curve was just n squared, right? It was the number of cards squared. And what did all of the, well, forget about the max and min. Let's think about the average. What did the average look like? Hmm? Yeah, it was right in between, but it also looked like an x squared kind of thing. Okay, it just was vertically squashed a little bit, and that squash amount is where that constant comes in. Okay, so another way to kind of think about this is, in essence, well, how many of you guys are either in or have taken some calculus? Yeah, couldn't we think about limits of these things? Right? What's the limit of f of n as n goes to infinity? Well, it ought to be infinity. If I give you infinitely many cards to sort, how long should that take you? Infinitely many operations, right? But what we're sort of interested in is how f and g grow relative to each other, okay? Okay, now you have to be a little bit careful with this notation because um, so some books use equal. So some books or people will write equals to O of n squared. I don't like that, and here's why. Because, well, would it shock you to learn that n is O of n? Why does that make sense that n should be O of n? Is n less than or equal to 1 times n for all n? I should hope so. Okay? You guys don't seem convinced. Cole, why is n O of n? Well, let's go back up to the definition. What does it mean for a function to be O of another function? It means that the first function is less than or equal to some constant times the second function. Okay, so accordingly, y is n O of n. Okay, so what's the function f of n in our example here? N. What's the function g in our example? Also n. Okay, so n and n are two positive functions. N is O of n if there's a constant so that n is less than or equal to a constant times n. Is there such a constant? Less than or equal, right? Yeah, 1, for example. 2, 3, right? There is such a constant. Okay, so do you guys accept n is O of n? Yeah? Okay, is n O of n squared? Sure. Is n less than a constant times n squared? Okay, so for n equals 1, n and n squared are the same value, right? But what about n equals 2? Is n less than or equal to n squared? Yeah, totes. Right? You could just graph the two things, graph y equals x and y equals x squared, and what are you going to notice? That starting at one of them is always bigger than the other. Namely, the square is bigger than the linear. Okay? All right, so here's why I don't like that notation to say equals. Because what might you conclude? Well, here, let me also write this. Does it come as a shock? For the same reason that n is O of n squared is O of n squared, right? Because is n squared always less than or equal to n squared? Yeah, right? Okay. All right, so I've got n is O of n squared, and n squared is O of n squared. Would you be tempted to say, oh, well, therefore n equals n squared? Because they're equal to a common thing, right? Like if I tell you A equals B and C equals B, what would you normally conclude? That A equals C. Well, that's kind of what I've got here. I've got A equals B, C equals B. What would it mean to conclude that A equals C here? That n equals n squared? That's a big old steaming pile of bullshit, as we say in Texas. Complete with the drawl, I reckon. Okay. Oh, come on. Now, don't I get more laughs out of that one? You're even from Texas. Huh? Well, okay. Yeah, and I guess, at the very southern end of Texas, there's not so many guys that are saying, have a southern drawl like this. You're speaking Spanish instead.
Yeah, we say, well, I know. We say, no mames.
What does that mean?
There is no like specific translation.
Okay. But you don't say that's a steaming pile of bullshit?
Un montón de mierda.
Yeah, well, mi español es muy malo, so I don't know. Okay, so this is why I don't like to use equals here. Okay, and so my preference would be to write something like this. So let me write it more carefully. What's the funky looking E? How many of you guys have taken Math 108 or anything in, right? So set notation, right? Something is inside this set. Like I could say, 2 is in the set of 1, 2, 3, or 5 is in the set of real numbers, something like that, right? That symbol, that's all I mean. That thing is inside of that thing, right? So O of n squared or O of n or whatever, these are big giant piles of functions, right? And my question is whether or not a given function is inside that pile of functions or not. Okay, so that's what I mean here. Okay, so what we've noticed here with our numerical stuff is, let me just re-emphasize this, is that on average, the bubble sort algorithm was what? It was O n squared. Okay, best case, an absolute worst case, okay, those are other matters, but best case, or sorry, not best case, average case, O n squared. Okay, does that kind of make sense? All right, are there other ways of sorting a pile of cards? Of course, right? There's just as many different ways of sorting them as there are people in this room. What we're also interested in, though, is what's the efficiency of those various different sorting algorithms, okay? So are there algorithms that are more efficient on average than the bubble sort method? Probably. And it turns out there are. There's one called quicksort, which you guys will be real surprised by this. Quicksort is actually fast. I know, right? Um, okay. But then there are other algorithms that are basically no better than quicksort. Okay, so a lot of the sorting algorithms are O n squared, and it's a little hard to beat that. Okay, right. So where are we going to kind of go with this? Well, this is where I'm going to start to turn you guys loose on an assignment or two, right? Is to look at a different sorting algorithm and kind of suss out what its order is, how does it work, and basically do the kind of analysis that we did on the bubble sort, but with a different algorithm. Okay, does that kind of make sense? Okay. All right. Well, it's any question, preguntas, and or fragens? Um, oh, I suppose I should also mention just a piece of business. Freshmen, today is the day I have to report midterm grades to the registrar, so you will get those here in a few days. Um, but for everybody else, I mean, since I just use Canvas, it's equally easy for me to put. So I just submit midterm grades for everybody. If you have a D or an F, then you will get on a hit list, um, and the goon squad of flying monkeys will be at your door sometime in the next week. Okay. All right. Hope you guys had fun. Uh, those of you guys who are online, hope you guys had a good time. Uh, we got all kinds of people on here that I don't recognize, and I will see you guys on Wednesday.